Hi, everybody. Welcome back to our afternoon session of the workshop on equivariance and data augmentation. So this is about six talks in the last session, and we're lucky to have Fabio Anselmi as our first speaker. So Fabio is a faculty member at Baylor College of Medicine and also affiliated with MIT, and he's done a lot of cool work on machine learning and neuroscience. And today he's going to talk about something related to that on neurally plausible mechanisms for learning selective and invariant representations. So please, Fabio, you can go ahead.
Thank you, Edgar. So today I want to tell you a little bit about how I thought with a simple model that these properties of invariance and equivariance could emerge in the brain. In particular, the first stages of visual processing in visual cortex. Oops. Okay, it's working. So as we have seen from previous talks, equivariance and invariance are really important properties for neural networks. But what I'm going to argue here, I mean, not difficult to do because there is plenty of experimental evidence that those are important properties also in the visual cortex. So as very hand-wavy examples, think about babies, which from early stages of their being in the world, they can recognize friends and objects and other type of stimuli in an invariant way. Okay, so this means that there is somehow an information processing in the visual cortex that is underlying this invariance. As an example of equivariance, I just propose here, but there are many of them, the retinotopic property of the retina mapping. By this, I mean that we have the following property. So an image whose pixels are nearby are mapped into a neural representation at the level of early visual cortex into activations of neurons which are nearby. So somehow, if you move the image, the full neural representation will move. Of course, it's a distorted one, but as a hint that equivariance is present also in early stages of visual processing. While in a convolutional neural network, equivariance and invariance are somehow natural properties, at least this is clear for translation because it is hardwired through convolution. How these properties emerge in the visual cortex is not clear. So in this talk, the subject of this talk is a first attempt, a very simple model on how to justify the emergence of these properties through very few biological plausible hypotheses and constraints. So the constraints and hypotheses I am restricting in this model are the following. I ignore feedback signal from higher visual cortex areas, and so I focus on the first 100 milliseconds of visual recognition. I ignore retinal preprocessing. As neural computations, I stick to the so-called simple complex model proposed in the 60s by Hubel and Wiesel, which I'm going to give you details in a little bit. And then, of course, neurons are going to update their weights due to the stimuli, and as a weights update protocol, if you want, I use a very common and well-accepted learning rule, which is based on the Hebbian principle. And then the main hypothesis here, which actually allows me to build up the mathematics, which I show you how to relax during the paper, is that the signal are transformations with respect to finite group. Okay, so is fit in the theme of this workshop. I consider data augmentation, and I consider a bunch of orbits basically. I just want to recall that there has been, of course, a lot of work about equivariance and invariance in neural networks, but also in the domain of neuroscience. I just want to recall a couple of papers here without pretending of being complete in any way. So the work about steerable filters of Verona in 1995 and the H-Max model in 1999, which somehow, have in their own construction some principles of invariance and equivariance. And then I would like to remind the whole work of James DiCarlo at MIT, with or without neural networks, trying to understand invariant object recognition in the visual cortex, not only in early visual areas, but also in higher visual areas. And of course, there are many other people, such as Edmund Ross, Tony Lindbergh, Carl Flintstone, and so on and so forth, which I just mentioned here. Note that I want to say is that I haven't found much, honestly, about the concept of equivariance in neural, in the representation in the visual cortex about objects. So this is one bit that I hope to give in this talk. So let's start from my constraints and hypothesis in the model. As I was saying, as a basic computational unit, I consider the so-called Hubble-Wiesel module of the visual cortex, which is composed as following. So we have a bunch of so-called simple cells. Here there are 3 of them, whose computation is simply a dot product between the input x and their synaptic weights, and then may be filtered by a nonlinearity sigma. And then the activations of these cells are somehow pooled, aggregated by a complex cell, which in this case is just summing up their activations, but you can think about many other type of pooling functions. Okay, so this is the type of mathematical object, if you want. I'm gonna concentrate in this talk, very simple. And what I'm gonna prove is that this neural signature of object or input x is going to be invariant and equivariant at the level of simple cells and complex cells if I adopt the type of hypothesis that I was mentioning before, and I think as stimuli, augmented stimuli with respect to some groups. Okay, but let's go and be more detailed. So just to give you a flavor of what a simple cell receptive field or weights can look like, think about Gabor-like receptive fields, okay? So those that are implementing a sort of wavelet transform. These are, by the way, often found on first layers of convolutional neural networks after training. Okay, so let's go to the main hypothesis here, which is about the stimulus space, which you can think as a data augmentation of stimuli. So in particular, what I consider is a finite unitary group, possibly unknown. Okay, so you may say, finite unitary, these are very strong constraints, of course. You can relax these constraints, but I just wanted to stick with these simple things just to give you the gist of the demonstrations and of the idea. Okay, so basically we're considering data augmentation with respect to an unknown finite unitary group. Of course, neurons update their weights during stimuli presentation, and as a rule for their updating, I consider the Hebbian principle, so neurons that fire together link together. And in particular, I'm considering a variation of that rule, which is called Oyer's rule, which is a form of a Hebbian rule in which the updates are normalized to have norm 1. But just to give you the gist of what this rule is doing is an online version for PCA. So what you have to keep in mind for the rest of the talk is that at equilibrium, this dynamical system will be able to converge for the weights, synaptic weights of the neuron, to the first eigencomponent of the stimuli. Okay, the one relative to the maximal eigenspace, the one relative to the biggest eigenvalue. Okay, So this is what you have to keep in mind. We can extend this plasticity rule, and I will show you how to do it later on. But just for now, this is the very simple scenario. So the main question of the talk is the following. Given those constraints and hypotheses, is this complex, simple complex module able to produce a neural representation of a stimulus which is invariant at the level of a complex cell, so the one that is pulling, and equivariant at the level of the simple cells. So keep in mind that I'm considering unsupervised learning first, and second, I'm considering a not known group a priori. So I don't know the symmetries. I just know that I have a collection of orbits. Okay, so let's draw some consequences from the hypothesis. From the hypothesis of the stimuli plus the hypothesis of learning, I can immediately deduce which type of weights my simple neurons are going to converge. So we can prove, it's quite simple, that the weights of simple cells converge to linear combination of elements of an orbit of G. Okay, so you pick up the first eigenspace of your covariance matrix, which is the one to which the weights are going to converge by Hoyer's rule. You pick up an element there, and you know that each other simple cell will converge to a linear combination of an orbit to elements of that orbit. So how can we prove it? It is very simple. I'm just show you the proof here because I think it's instructive. So, and give you the idea that is behind it. So if these X are my data augmentation, so I augmented the templates, the patches, if you want, the stimuli T with respect to the group G, then if I build up the covariance matrix, you immediately see that is basically an averaged version with respect to the elements of the group G of the covariance matrix of the representatives of the orbit, so the T1, TQ. Okay, and the nice property is that you can prove in one line this covariance matrix commute with all the elements of the group. Why is this interesting? Because if omega is a solution of the eigenequation, then you can immediately see that another element of the orbit is a solution, and so for any linear combination of it, since C is linear. You can prove the opposite, and in particular what you can prove is that each possible simple cell weight is in the linear combination of elements of an orbit. You can extend this nice property of commutativity, and if you want equivariance of the dynamic rule, to a more generic class of plasticity rules. The important thing is that those are some permutation invariant combination of the activations of the simple cells. So this product here, this guy here inside the F is just an activation of a simple cell, and then you sum, for example, you do any type of transformation, sorry, any type of operation, which is permutation invariant. If this is the case and you have full orbits, that augmentation, what you can prove is that the dynamic is equivariant, okay? And therefore, if omega is a solution, so is any element of the orbit. I think this is an interesting property, which I've shown here in a very specific case. Okay, so now that we know which the receptive fields, the weights of the simple cells, the next question is what is a complex cells aggregating? So which type of simple cells is a complex cells going to aggregate, to pool? And to understand this, I just refer again to the Hebbian principle of phi together, link together. So the idea is that under a stimulus, which I think to be just an orbit of another, stimulus X, sticking to the hypothesis, which are the cells that fire most under this stimulus, under this bunch of stimuli, those will be the ones that are pulled by the complex cell. So suppose that omega bar is the weights which are relative to the simple cell, suppose it's this guy here, that is firing most under the first stimulus in this orbit, so X, okay? Now, the question is, which will be the next simple cell that fire most under the second element of the stimulus, which is G2X. And this is a very simple, algebraic problem, and you can immediately see that due to the, properties of invariance under unitary transformation of the dot product, that the cell that is going to fire most is going to be G2 omega bar. So just to summarize, what you can find with this very simple algebraic reasoning is that the complex cells will learn to aggregate over simple cells whose weights form an orbit. And this is, a very simple argument that I can make it a little bit more precise and complex, but this very simple argument allows you to justify the properties of invariance and equivariance, the emergence of such properties for your neural signature. So just to summarize, the symmetry in the stimulus space due to data augmentation are somehow inherited in the weights of the simple cells in the following form. So any weight to which is going to converge a simple cells after being shown the stimuli is a linear combination of an orbit. And then among these simple cells, the ones that are pulled by a complex cells through this Hebbian learning, Hebbian principle, are orbits. So just this blah, 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 I can, summarize it with a formula and say, well, instead of having generic omega here, you have an orbit. That is the gist of what I found so far. So having this particular form of neural representation immediately allows you to understand how equivariant and invariant properties emerges. So just for simplicity, organize the weights of your simple cells in the matrix. So this is a matrix whose columns are vectors, and those are an orbit of omega. Okay, so the simple cells response, you can write it as the application of omega transpose, so the linear operator of the weights onto the stimuli, and then you have a pointwise filtering. What you can immediately see is that if you, instead of calculating the neural representation for X, you calculate the neural representation for GX, due to the closureness property of the group, this will be transformed into basic a permutation of the simple cell responses. Okay, so the action of transformation at the level of the stimulus is a permutation at the level of the activations. And so this is a form of a permutation equivariance. This is for simple cells. For complex cells, instead, you can immediately see that the response is invariant, since the way in which is aggregated is a group average. And so just a simple change of variables will show you that the neural signature for X is equal to the neural signature of the transformation of X. Okay, this is, of course, you can generalize this to a much wider class of aggregating functions and nonlinearities, pointwise nonlinearities. Okay, so far I've shown you how the properties of equivariance and invariance can emerge from very simple biological constraints and hypotheses. But what about selectivity and discriminability? Of course, if we suppose that the ventral stream, which is or the visual cortex can do invariant representation, there are many ways of doing invariant representations, also trivial ways. You can have the function that is mapping everything to the point 0, and this is an invariant representation, but it's clearly not very useful. So what we would like to have is a sort of discriminability. So the ability to be able to, in other words, to produce a nice, proper quotient space with respect to the transformation. In other words, two elements would like that the neural signature is capable of, compress to two points which belong to the same orbit into the same point, or tear apart 2 points that belong to different orbits. So this is the discriminability or selectivity part. How can we achieve this? Of course, when you do, group averaging, maybe only with one set of neurons, you lose information. It turns out, and I think this is related with something that has been already said in previous talks, that we can somehow recover this loss of information, considering instead of a single nonlinearity, a bunch of nonlinearities, which in this case, just to show you some results, I just consider to be a step function of the heavy side, whose parameter is the threshold, okay? So what you can prove is the following. If instead of having one complex cell, you have a bunch of them, in which each one is different from by the threshold, then if you build up the L2 norm distance between the neural signatures of these stimuli, you can see that you can prove that the distance is 0 if and only if the two elements belong to the same class of equivalence. This is, of course, in the limit where Z is continuous and you have infinite number of them. But you can think about, relaxations of this constraint in form of discretizations. Okay, so I've done some simulations just to prove how this theory applies to real data. So I generated two artificial data, just do data augmentation with cyclic group and dihedral group, just to have an abelian and not abelian group in very low dimension. I think this was 6 and this was 12. And then I generated data, instead to have a more concrete example, with a finite group of rotations of natural patches. I generated a bunch of orbits. I calculated the distance between the neural signatures, and these plots are the distribution of those distances for elements that belong to the same orbit, for which I expect the distance to be 0, and for elements which belong to different orbits, which I expect the distance to be different from 0, because I want to build up a proper quotient space. And that's what you see here. This is the logarithmic scale, and this is the distribution, the intra-orbit distances and the inter-orbit distances. In the other plot, just to prove how important is the role of nonlinearities in the selectivity, I just plot the distance, how the distance between two elements that do not belong to the same class of equivalence change in function of the number of thresholds of my nonlinearity, so the number of nonlinearities. Overall, these plots, let's say, confirm the theory, even if I have to say, that if you go on real data, the things are less clear, but still we have some good separation between the distribution of the intra and inter orbits. Okay, so before concluding, I would like to, make a quite, let's say, hand-wavy argument about how you can go beyond groups and analyze, transformations which do not have a nice structure. So as I was saying in the panel before, consider, for example, a diffeomorphic transformation of a face. Well, what you can think about is that if the transformation is smooth enough, at least locally, you can around the point, you can approximate the transformation using the generators of the Lie group on the tangent space around that point. And you can consider those, having a group structure and apply the kind of very similar arguments. This is my intuition, hand-waving intuition that I wanted to give you about how to generalize this. So the idea is to, if you have something which is a transformation of an object which do not belong, do not have group structure, well, look locally enough and you will find it. That's something. That's the type of argument that I want to propose. Okay, so just to jump to conclusions here, I've shown you that under a very simple biological hypothesis and constraints, we were able to explain the emergence of equivariance in simple cell responses, invariance for complex cell responses, and discriminability with respect to the transformations. Okay, so if you're interested in reading more about this, we recently published a paper in the Journal of Mathematical Neuroscience. So before saying thank you for your time and attention, I just want to show you something which I hope will be interesting for you. You see the screen, right? So we just opened a research topic around a month ago about how can we use symmetry as a guiding principle in understanding neural information processing in frontiers of neuroscience. So I hope that you may find this interesting, and please find the time if you want to go and read what we propose. Is, by the way, something in collaboration with Tommaso Poggio and Kit Patel and Andrea Tacchetti at DeepMind. So I hope you find this interesting, and please take a look. And with that, I'm happy to take any question.
Great. Thank you very much for the very nice talk. Just very quickly, you can post that link to the frontiers in the chat so that people can access it afterwards. And so there is a question from Stéphane Denis saying complex cells are only invariant to local translations. So how do you think about accounting for the local invariance, right? That's not the global invariance.
Yeah. So what I said right now, of course, is a little bit of abstraction. But in reality, what you do have, I was thinking to do data augmentation. If you think to do data augmentation with respect to the translation group, there is no hope because it's not a compact group. So what you will have is, in the optimistic hypothesis that you will see a bunch, let's say a part of an orbit. And therefore, your complex signature will be approximating to an invariant representation. And by that approximation, I mean, the approximation is going to be as good as your translations are small. And that's what comes, about this observation. So basically, you don't observe the full orbit, you observe a part of it, and therefore you can hope for having a robustness to translations. And you can write the theory in this form, it's just less clean, basically.
Okay, great. Thank you very much. So I also had a kind of small question, but maybe just do you have a sense of like how many, like in the result where you had that you can actually represent the orbits when you have infinitely many z's? Do you have a sense of how many finite z's is enough to represent the orbit?
Well, I wrote a sort of concentration inequality, so it depends. Actually, I don't remember exactly how it scales, but I wrote a concentration inequality, so I have to look at it. Okay. But the idea is that, to deal with sampling of orbits, to deal with, you adopt two things. One is the concept of locality, and the other one is a concentration inequality. And of course, you will have approximations. I think it scales with n, but I have to look at one.
We can check your paper. Yeah, great.